computer. Okay, so like I said, we're going to be talking about pHs and acidic and basic solutions. Tomorrow, there is going to be an extra credit opportunity. So make sure that you come to class. I'm going to be posting an announcement about this as well. And it has to do with there's going to be an activity that you do on your own, and then we're going to break off into breakout rooms, and you will do it as a group. Excuse me. So look for that to happen tomorrow. In the meantime, though, I'm going to blow this up. Beginning and what we are talking about today is found in chapter number 7. If you want to look at the references, we're going through 7.1, 2, and 6. And part of this, or a big part of this, is all about kind of squaring terminologies, aligning like the actual definition of an acid and a base, and comparing and contrasting that with maybe the way that you've heard that term used outside of any sort of science class. So we will go ahead, we're cracking on that. We're in chapter 7, so we've got this and 8. We'll finish 7 tomorrow, and then we'll do 8 next week. And we're only doing 2 sections from 8. So when you hear the word acid or base, what comes to mind? Personally, whenever I hear acid or base, I always think about a movie. And I always think about movies, and I think about like I guess you could just say like the villain or the antagonist in a movie. They're going to use acid to destroy the city or something. You know, that's as vague and general as a threat. But I always think of like an acid as being used as like almost a weapon of sorts. And then my next thought is like I think about stomach acid. And then last but not least, I always think about battery acid. So those are the 3 contexts that I think about acids. And then after that, you know, I think about it in the context of a chemistry class. And that's what we're going to be kind of addressing here. Now, there are some acids and bases that you come across on a day-to-day basis. For instance, if you take a vitamin C supplement. Oh, vitamin C is commonly known, or also known as ascorbic acid. And you might also hear it referred to as ascorbate. Drano is a base. That base is sodium hydroxide. If you have a pool, then you probably, or if you've ever worked near a pool or anything like that, or know someone with a pool, chances are you've had to use an acid, add an acid to neutral or to adjust the pH of that so that it's safe for you to get into. In the event that you've been to a pool where the pH has not been adjusted, then you might see like an algae bloom or something in there, or you might jump in and get out and be like, oh, it's really slippery. And that slippery sensation so that sort of slick, slippery sensation is what you typically feel whenever you're exposed to a basic environment, so a base. So my point is that if someone has a pool and they have not treated it, they have not adjusted the pH, then it's going to have a basic pH, and so then they have to counteract that by adding HCl. Vinegar that you get at the grocery store, at Target, HEB, whatever, that's acetic acid. And acetic acid is commonly referred to, or in scientific terms, referred to as a weak acid. But one thing that we'll talk about a little bit is that when you hear a weak acid, or the terms weak acid or strong acid, don't fall into the trap of thinking like, oh, that can't cause harm. Instead, that has to do with like a technical definition. A weak acid, if you poured that on an open wound or something like that, it's going to feel painful. It's going to be uncomfortable, whether that's a weak acid or a strong acid. If you have a cut that's exposed to an acid, it's probably going to hurt. Then we've got this one over here, ammonia. Ammonia is the active ingredient in Windex, as well as a number of other cleaning agents. And that is a basic solution. So ascorbic acid, vitamin C. Drano, for example, the active agent is sodium hydroxide. HCl is used to adjust the pH of pools. And acetic acid is vinegar. And then last but not least, ammonia, not ammonium, ammonia is regularly used in cleaning agents like Windex. Now, some of the properties of acids and bases. Well, first of all, an acid is going to taste sour. For instance, if you ever get if you got, 3 or 4 vitamin C pills and you bit into them and tried to chew them, then it's going to be pretty tart. It's going to be pretty sour because of that ascorbic acid. There's nothing else that's doing that. It's just the ascorbic acid that's causing that. Now, acids can dissolve active metals. Now, this is a certain kind of designation. Does it dissolve all metals? No, it doesn't. There are some metals that are resistant to exposure to acid, and those are not going to kind of break down. Now, when you hear that right there, acids that are resistant to, or sorry, metals that are resistant to acid exposure, I think a really good example of that would be something like gold. Gold, for its expense, or due to its strength and its resistance to being degraded, it's expensive because it can resist that. Acids react with a base to form water and salt. Now, this is it's not really a joke. It's a joke, but nobody really laughs at it. And not because it's just kind of not really a great joke. And that is, whenever I'm introducing acids and bases, I say, oh, what's an acid? And someone would say, oh, well, it's something that tastes sour or dissolves metal. And I say, yeah, you're right. And then they say, okay, well, what's a base? And they'll say, well, a base is something that tastes bitter or heck, feels slippery. And I'd be like, yeah. And then I say, not right, but I say, what's a salt? And then someone says, oh, well, it's what forms when an acid and base react with one another. Say, aha, no, no, no. And then they're like, what? And I say, yeah, what's a salt? And then just as someone's about to answer, I say, it's a crime. Because I'm pronouncing assault. Anyway, I won't write that out. Anyway, so yeah, that was kind of the response I thought. So these are properties of acids, and then bases taste bitter, feel slippery, they react with acids. The last thing is acids and bases can turn a piece of paper, specifically blue litmus paper or red litmus paper, red or blue respectively. Blue litmus paper is going to give you a way of detecting an acid. Red litmus paper will give you a way of detecting a base. Now, there is another type of litmus paper that is neutral litmus paper, but red litmus paper detects bases and blue litmus paper detects acids. Here's an example. This is blue litmus paper, and whenever it's doused or inserted into this solution, it turns pink, or it turns red, pink, whatever. So that blue litmus paper it turned red. So this solution right here is an acid. Now, this right here is red litmus paper. Red litmus paper in whenever it's inserted into this solution right here, well, it turns blue. So what does that mean for this solution? It means it is a base. Now, an active metal in acid. Okay, so let's go ahead and take a look at that. And I gotta switch to no. So what's important to recognize about this is that here is a solution of hydrochloric acid. When you, this is an important thing to think about and recognize. Whenever you look at an acidic solution or a solution of hydrochloric acid, what does it look like? Is there anything that stands out like obviously that is an acid? No, it has no pigment to it or anything like that. Acids and bases typically don't have any sort of visible cues. Instead, the cues that you can get from them are their chemical properties. So here what we have is an HCl solution and a magnesium ribbon. So magnesium is a metal that, oh, look at that. It's bubbling, but what's difficult to see is that over time, it's going to basically degrade. It's going to completely degrade, and there's not really going to be anything left. Now, that is an example of an active metal, so a metal that can react. Now, if you think about the periodic table and you look at the left-hand side, that's where you're going to find your most reactive metals. Magnesium is a reactive metal. Gold is not a reactive metal. So if you got hydrochloric acid and you dropped like I mean, this wouldn't be really it's not really too much of a harm or anything like that. But let's say that you had a ring that appeared to be gold. And then you had two rings. One appeared to be gold and one you knew was not gold. If you took those two rings and you dropped them into a solution of water, nothing's going to happen. If you took those two rings and dropped them into a hydrochloric acid solution, the one that looks gold, well, you'll know if it is actual gold if it does not begin bubbling. I'm sorry. If it does begin bubbling, what that tells you is that it's an alloy. So that means it's gold and something else, gold and iron or something like that. That's one of the things about gold. That's a physical property about, or that's a chemical property, I'm sorry, a chemical property of gold that makes it valuable, is that it can withstand any sort of corrosion brought on by hydrochloric acid. It's not going to react with hydrochloric acid. And that's not to say like, oh, you see hydrochloric acid everywhere, but that's an indicator of its overall strength. So what that means is that if you have a gold ring or something like that, you can wash your hands, you can expose that to everything in your everyday environment, and it's not going to get degraded. It's not very chemically reactive. Physically, gold has some other properties. For instance, gold is very bendable, it's very malleable. But here what we have is an example of a metal that's very reactive in a hydrochloric acid solution, and that metal would be magnesium. Now, theories of acids and bases. Think about this as kind of like definitions, and these are refined definitions. There was an old definition of an acid that was developed by a guy whose last name, or a person whose last name was Arrhenius. And so for a long time, if somebody said an acid or a base or described something as an acid or a base, they maybe were they were probably using the Arrhenius definition. And what that means is that this compound that was described as an acid produces a hydrogen ion in water. This hydrogen ion is commonly also known as a proton. If it was an Arrhenius base, it would produce hydroxide ions in water. Now, one of the challenges and limitations of these definitions is this does not explain the basicity, the base properties, the basic properties of all compounds. For example, NH3 is a base, but this Arrhenius definition, it doesn't address that. Because if you added NH3 to water, you're not going to produce hydroxide ions. Now, this only applies to an aqueous solution. If you remember, whenever we were talking about substances, NaCl, for instance, we talked about solids, and then we talked about H2O as a liquid. That's an L, not an E. And then we can also talk about HCl with the AQ, meaning aqueous, meaning that's dissolved ions in solution. Now, these are kind of the old definitions. I think that you will probably have a question about an Arrhenius acid or base, but that will really kind of be a definition, or maybe address the limitation. What is known as the Bronsted-Lowry definition of an acid or a base is the more commonly used one to date, and it's the newer one. An acid is a proton donor. So if you take something like HCl, what HCl is that HCl, when you add it to water, it will separate into H plus and Cl minus. So it donates H plus. So that's why it's a definition. Now, if we look at something like NaOH, well, NaOH will separate into two things. Separate into Na plus and OH minus. Now, this is a base because this OH right here, what it's going to do is it's going to take on a proton. If you have H plus and OH minus, and those two things come together, you've got HOH, or simply put, H2O. So that would be a base. So moving forward, if I talk about an acid or a base, I'm using that Bronsted-Lowry definition. If I ask you about the Arrhenius definition, I will say an Arrhenius base will produce what in water? And your answer would be hydroxide ions. An Arrhenius acid produces proton, or produces what in water? And that would be H plus. I could also ask something like, the Arrhenius definition has a blind spot for what compound? And that would be something like NH3. Okay, so here what we have is a pair of reactions in water. And these reactions are HCl, H2O. And what do we get from those? We get Cl minus, and oh man, what on earth is that? O plus. So if you were to write that as a formula, you'd write out H3O plus. Well, that's kind of odd because just a second ago, I said H plus. I didn't say anything about H3O plus. This is known as a hydronium. Hydro-N-O. Hydronium. Hydronium ion. Because remember, an ion is a species, it is a molecule with a charge. So this is an ion because it has a positive charge. It's an example of a cation. Now, this hydronium ion is used as an equivalent to H plus. Because H plus is not going to exist in a solution, but H3O plus will exist in a solution. So we will use hydrogen ions and hydronium ion, these two terms, interchangeably. And it's pretty common to see H plus be representative of H3O plus. Now let's go back. We have HCl reacting with H2O. Okay, so what happens is this hydrogen right here is donated, which makes sense because HCl is our acid. It's donated. HCl, if we think about the parts, if we think about that as a whole thing, look at our products. We have Cl minus. Cl minus on the product side does not have H plus. So that H plus is donated, in which case we end up with that H3O plus. It's donated to our H2O. Now, if we look down at our next reaction, we have NHHH, so NH3 plus H2O. Okay. Now, we have one hydrogen that is highlighted here. So if we, this takes a little bit of, let me see if I can get it real quick. Those for exam 2. The specific, yes, perfect. That's exactly what I was thinking about. Okay, so when we look at, let's just ignore this for a second. We're trying to predict, okay, we've got, or what we're trying to predict is NH3 or is H2O going to give up a hydrogen? Is it going to give a hydrogen to the other? So essentially, is H2O going to act as an acid and therefore NH3 acts as a base, or is NH3 going to act as an acid and H2O is going to act as a base? That's what we're trying to figure out. We've got a clue here of H2O, and that H that's both underlined and highlighted in pink or magenta. But man, it's kind of, I mean, that's our clue, or that's not really a clue. That's just kind of the information given away. But do we have anything else in our kind of our mind that really can take us back to answer anything about the different atoms and bonds that they like to have? The answer is yes, we do. So if we go back to, I believe it was exam 2 material. When we go back to exam 2 material, one thing that we can see is that nitrogen likes to have 3 bonds and a lone pair of electrons. Now, that's kind of what it likes to have. If we jump over, sorry, I gotta switch my share again. If we go here, we can see that, well, yeah, nitrogen has those 3 bonds. And so, it probably doesn't want to give up a hydrogen. And that mentality, that rationale would be would be correct and sound. Now, in addition to that, whenever water gives up that hydrogen, nitrogen accepts it, we're going to end up with a positively charged nitrogen and 4 nitrogen-hydrogen bonds. We're also going to end up with a hydroxide ion. I'm going to label that hydroxide. So that's a hydroxide ion, and this right here is ammonium. Now, a fair question there is, okay, well, that figure that you showed, the you being me here, has, well, oxygen likes to have two bonds. Why don't we have oxygen keep those two bonds and nitrogen drop down to two bonds? Why not? Or why don't we give the hydrogen from NH3 to OH or H2O to make that H3O plus? And the answer is because of the kind of, let's see, what's the best word for this? It's almost like I'll say dynamic. It's because of the dynamic and flexible nature of water. Water can act as an acid, so it can give up a proton, which is what it's doing here. I'm going to put a big letter A right here. It can also act as a base, which is what it's doing up here. Now, the powerful thing about what we're seeing here is that in both of these reactions, we have one thing acting as an acid and the other thing acting as a base. Ammonia, NH3, acts as a base, and water acts as an acid. Water, in our two different reactions, in one case it acts as an acid, and in the other case it acts as a base. That's all dependent on what the other species is. HCl, in particular, is a species that is a strong acid. So that means that it really hates being with that chlorine. So that chlorine likes to form a chloride ion, which is what it does right here. So understanding that in these reactions, we're going to have one thing acting as an acid, one thing acting as a base. Whichever acts as the acid, the other thing is going to act as a base. Now, to evaluate solutions and to evaluate substances, we will use what's known as a pH scale. And the cool thing about this, to me, is that if we look at this list, like gastric juices, okay, so everyone's got, some solution in their gut. A soda has an acidic pH of about 2.5. That's pretty acidic. If you go to the dentist, chances are your dentist is going to tell you, hey, be careful with drinking sodas because of the acid content. They'll also tell you, be careful drinking, that's right, coffee because of the acidic content. In addition to that, they also have dyes which can stain your teeth. Oranges are acidic. Tomatoes are a little bit less acidic. Urine has a pretty broad range of acidity, which when you think about that, what does, like, for every single thing that you drink, whether it's a soda or water or a beer or anything else under the sun, tea, if you drink a soda and then you eat a bunch of oranges and tomatoes, your urine is probably going to be a little bit more acidic. If, however, you don't drink any soda, cola, pop, whatever, and instead you try to siphon all the salt out of seawater and you drink a bunch of seawater, so you get rid of the salt because that would be hazardous, that would be deadly to you. That's a more basic solution. That's going to make your urine pH slightly more basic. So your pH is going to be a little bit higher on your urine. So this has a range because of the fact that you're drinking and consuming lots of different things. And those different things that you eat and drink are going to influence the output that your body makes. Now, all of this is going to be neutralized and filtered by going through your stomach and going through your kidneys. And so that's going to cause a pretty dramatic change. So Some of these things you'll see on a sorry, some of these things that will, or some of these different solutions will have a pH range that is more basic, and others will be more acidic. Now, one of the common misconceptions that people have is, oh, well, basic, a lower pH is bad, is hazardous. Or sorry, acidic. Acidic with a lower pH is bad, it's hazardous, it can hurt you. Whereas basic is the opposite of that. Well, the opposite of bad is good, therefore basic is good. No, that's not the case. You can experience what are known as base burns. And base burns, I would argue, are maybe a little bit more concerning because, like I said previously, like what was highlighted here, your initial sensation when you touch something that's basic, especially if it's on your fingers, is, it'll just kind of feel like slippery. And it's kind of a weird sensation. It's almost like you, yeah, it's almost like you have soap or something on your fingers and they'll slip around. But that's kind of an illusion. So you'll do that and you'll be like, okay, oh, no big deal. It's just I got some soap on my hand or something like that. And then an hour later, your fingers are all red. Why is that? Because that base has caused damage. It has killed skin cells. It has caused damage to your fingers. So if acid, don't go into this with the mindset of acid bad, base good. That's not true. Acids and bases are opposites of one another because of what they do. An acid is going to donate a proton, whereas a base is going to accept a proton. That's what makes them different from one another. Now, Zoom poll. We've got a solution with a pH of 10 is A, acidic, B, basic, C, neutral, or D, toxic. Like the Britney Spears song, Toxic. So we have 7 participants in class. 14% of the class has participated in the first 20 seconds. Okay, 28%. We've doubled our numbers. Let's see if we can get to 4. We got to 4 yesterday pretty consistently. I can give you another 15 seconds. Okay, we got 3. 6, 5, 4. Okay, we got 4. Let's see if we can get 5. 3, 2, 1. We did it. We did it. Not only did we get to 5, but we got to 100% correct. You're right, it's basic. Good job. Okay. Now, next up is, what does this mean? So calculating pH is kind of tricky. So the pH is kind of your measure of a solution, your measure of the basicity or acidity of a solution. And that is equal to the negative log of the hydrogen ion concentrations. Oh man, what? Well, remember that hydrogen ion concentration is the same as your hydronium ion concentration. And I know that you probably heard that in the same way that I heard it for the very first time. And that was like, oh, okay, hydrogen ion concentration. Don't follow that. Oh, now you started using hydronium ion concentration. Great. Another term that doesn't make a lot of sense to me. Well, let's jog back for a second. And I'm going to clear all my beautiful markings on this slide. A solution is acidic if it leads to, or a substance, let me rephrase that. A substance is acidic if it leads to the production of more of this right here. HCl. When you add that to water, it reacts with water and makes a bunch of this right here. So anything that leads to the production of a bunch of that H3O plus or H plus is going to be acidic. Now, there are substances that are not necessarily you know, purchased in a chemistry lab or used exclusively for a chemistry lab that will produce that right there. Certain metals. If you go to your tap water and to that tap water you add some, let's not say baking soda, but let's say that you got some let's say that you got some water, you put it in a blender, and then you got some bread. You got a piece of bread from a loaf of bread, and you blended it up. Okay, you blended it up and you made it something that is a a solution. It would not be very tasty, but that solution is going to have a pH that's different from that pure water because that bread, whenever you sheared it and spread it out and everything like that, is going to lead to either the production of more of this or more of this. If it leads to the production of more of this, what does that say about that bread? That bread is acidic. Now, all foods are going to be acidic or basic. If anyone's familiar with sports superstar Tom Brady, he has a very restrictive diet and something like he doesn't eat strawberries or doesn't eat nightshades, doesn't eat and I only know nightshades because of him. It's like bell peppers. You don't eat bell peppers. Why? Because they're acidic. And the way that that's deduced is, well, you take that, food, you blend it up, and you see, does it produce more of this or more of this? And if it produces more of this right here, where I put my X, then that food is considered basic. If it produces more of this, where I put my Y, that is an acidic food. Coffee is acidic. Bell peppers are probably acidic because, well, what do they have a lot of? Just as an example, bell peppers have a lot of ascorbic acid. That's the specific acid that they have. Okay. So essentially, there's a way that you can measure the concentration of these hydronium or hydrogen ions. If you take, using your calculator, the negative log of the concentration of hydronium ions or hydrogen ions, you can figure out the pH. So all that you do, you can do this in my calculator, and I will share my screen with y'all, is, let's see, we'll share this screen right here. Perfect. So let's say that you figured out the concentration of hydrogen ions in a solution was 0.003. Well, you would take the log of that, the negative log of that. So notice how the calculator function, it says negate log 0.003. That would give you a pH of 2.5228787 and so on. So what is that pH? Is that acidic or is that basic? Well, that would be an acidic pH. Now, that is the hydrogen or hydronium ion concentration. If that concentration went up, so just imagine that 2.52, 0.003 yields a 2.52 pH. Okay, now what I'm going to do is I'm going to clear all this, and I'm going to say, let's say that the hydrogen ion concentration, let's say that that hydrogen ion concentration increased. So I'm going to go with 0.00006. Okay, so that's doubled. I've doubled my hydrogen ion concentration. Before I plug this in, what do you think that means? So an acidic solution or a substance that is an acid leads to the production of more H3O plus or H plus. Our hydrogen ion concentration went from 0.003 to now it is 0.006. So that substance made more of those hydrogen ions. What does that mean for my pH? Did my pH go up or did it go down? Well, if it went up, then I would expect, or that would mean that my substance is more acidic. And lo and behold, that'd be 2.221. So 0.006 is 2.22. So that's how you calculate pH, by knowing the hydrogen ion concentration. Now, that can be done with the Windows calculator. I believe it can also be done with the calculator that is used in Proctorio. The log function is there. Now, to figure out the hydrogen ion concentration, you can do the opposite of that by taking whatever your pH is and raising that to the negative pH. So if your pH was 2. Or let's say your pH was 3.6, you would say 10, and then you would use the caret function, negative 3.6. Plug that in, and that gets you your hydrogen ion concentration. Zoom poll. Okay, last time we got 5 people. I think we can do it again. I can give you till 45 seconds. So we got 33 seconds left. One person has answered. 2. Spoiler, those 2 have gotten it right. I'm sharing the screen. Okay, we got 5 people. Can we do 2 more? Okay, time's up. The answer was no, we can't. Okay, so we have 2 answers. One is 3 and one is negative 3. Okay, now I'll let you know that I'm pretty happy with this overall response. The correct answer is B, 3. The person who answered negative 3, what they probably forgot to do was include that negative to negate that negative 3. So they probably plugged it into the calculator, but just that last negative function. So very close. That's why I'm happy with this. Now, let's jump back for a second. This is the typical range. This is the typical range on a pH scale from 0 to 14. Can the pH of a solution be less than 0 or higher than 14? Yes, it can. What is the likelihood of that happening? Very low. Most any and every solution that people work with in any given day, it's going to fall within this range of 0 to 14. It's probably not going to exceed 14, and just as likely, it's probably not going to go below 0. So those are, I would just keep that in mind whenever you answer a question like this. Again, that's not to say that it cannot be outside those ranges, but for what we're doing in this class, it's probably going to be within this range. Now, it's also pretty typical that your pH would not, that's not to say like, junior, senior level chemistry classes, you might work with a solution with a pH higher than 14 or lower than 0, but it's very rare. Okay. Yeah, we've talked about that. So this is another perspective on how to look at the litmus paper. The blue litmus paper turns red, indicating a pH below 7. And the red litmus paper turns blue, indicating a pH above 7. Now, one of the limitations and challenges with this is that you can't really quantitate this, and you don't really look at it as, oh, well, this is so much more blue. So that's one of the tough parts about this measurement. That you just it's tough to do that. It's difficult to have that measurement. So when we look at a solution, when we look at a solution and we're visualizing it, what's taking place at that molecular level is an important thing to kind of wrap your mind around. So that one. Sure. Okay, so here what we have is a pair of water molecules and a hydronium ion and a hydroxide ion. So these two things are in what's known as an equilibrium. So they will go back and forth, in which case we're going to have a pH of the solution, which is neutral. It's going to be 7 exactly. Now, what I'm going to do is I'm going to get some strong acid and add that. Now, all of a sudden, what do I have a greater abundance of? If you look at this, we've got 4 different species that we kind of want to wrap our mind around. We've got this HA, which is our acid. We've got H2O. We've got A minus and H3O plus. I like to think about this as I'm going to use an acid, HCl. That HCl, what we saw previously was that HCl donates a hydrogen ion to make H3O plus. What's left behind is Cl minus. Now, look into that magnifying glass. How many H2Os do you see? Very few. In fact, I don't see any. And that's not a mistake. That's not your eyes, you're just missing them. There aren't any H2Os because what they've basically been, or they've kind of been commandeered to make a bunch of this H3O plus. Now, another way that we could kind of visualize that and quantify it is to look at a graph. We've got HCl. We have basically none of that. We have a higher concentration, or we have quite a bit of our A minus and H3O plus. So this particulate view right here is a good idea what's happening at a neutral at an acidic pH. Now, if by comparison we add a strong base, well then what we're going to get a lot of is we're again not going to have much of our or we're going to have a bunch of that M plus and OH minus, that hydroxide ion, those hydroxide ions, which I can draw, square them. We've got a ton of these. How many of these things do we have in there? Basically none. We've got this, we've got this, here, and here, respectively. And that gives us a pH of 12. So I like that because it's a good cue of things. We could also do that with pH paper, but I just like to, I like to have the quantitative measure with that. Yeah. So this one thing that I do want to highlight that's a little bit different is this pH color key that we're showing here. That's for what's known as universal litmus paper. So that litmus paper is great because it can tell you if the pH is approximately 5, 6, 7, 8, and so on. Now, it's tough to discern a solution with a pH of 0 versus a pH of 1 or 2, but it's nice to be able to compare pH of 0 and pH of 4. This universal litmus paper is useful because it quantifies the pH of a solution, whereas the red or blue litmus paper is just going to tell you if the pH is below a certain amount or greater than a certain amount. It's not going to be as quantifiable. So universal litmus paper is quantifiable, whereas red or blue litmus paper is not. Now, one cool thing that people do from time to time is they use red cabbage. Basically, what you do is you blend up a red cabbage with water, and you can make kind of an indicator solution, a pH indicator solution with this red cabbage juice. So if you were to take that red cabbage juice and add it to a basic solution, it would look like that. An acidic solution, it would look like that. Now, here's a display of that, or here's an example of that. That red cabbage juice added to ammonia or baking soda, or, well, here's pure water. Um, Essentially, these are the things that these are the different pHs that you can get. And it's basically kind of validation of these. So your vinegar is a red, so that's going to be kind of in this range. It's probably going to be closer to that one more than anything else, just based on a visual comparison. Now, there's another test that you can do with this PhET simulator. So this simulator, what we can look at is, switch my share. So here what we have is a solution that is neutral. When we check the pH, it measures at 0. Now, if I add to that blood, I'm getting 1/2 liter of blood. I have a pH of 7.4, so it's higher, so it's slightly more basic. So your blood has a pH that's higher than a neutral pH, so it's slightly basic. If I add water to 1 liter, my concentration of hydrogen and hydroxide ions, well, it's changed. So my pH has changed. So this is kind of looking back at what we talked about the other day, and that is dilution. If you dilute a solution, well, then the pH is going to change, because when we added pure water to this blood, we didn't add any more hydrogen ions. Instead, we added just pure water, which is not going to really react with anything to produce anything new. If we add soda pop to this, okay, then just the water down there. So think about, or I think that it's helpful to think about this in terms of, like, what you like, let's take dental health for an example. If your dentist says, oh, well, you need to, stop drinking soda, and you're like, I refuse to stop drinking soda. Well, then you can kind of find a compromise, and that is say, okay, well, I will do a couple of things. I will cut down on the amount of soda that I drink, but also I'm going to drink a lot more water. So I'm going to get rid of that, and I will add more water to basically work towards neutralizing or reducing the acidity of all of that soda that I'm drinking, or all of that soda pop that I'm drinking. So, yeah. But you can also see that we're drinking, I'm going to restart this. So, I'm drinking orange juice. Okay, so I just drank 1/2 liter of orange juice, which is a pretty healthy amount of orange juice. And I'm going to add water, 1-to-1 dilution. My pH went up to 3.8. I'm going to drop this down to 1/2 liter. I'm going to bring more water into the equation. My pH goes up. So right now, what I'm looking at, if my math is correct, I drank 1/2 liter of orange juice, and I now drank 1 liter of water, 1.5. I'm going to keep doing this until my pH is closer to neutral, or is neutral. So now I'm at 2 liters of water drank, 2.5. 3. And I'm not going exactly to 0.5 and everything like that in 1.0. 3.5. Four. 4.5. 5. Oof. 5.5. This should do it. 6. Oof. 6.5. 7. Ouch. 7.5. Okay. So really what I want you to take away from this is to offset anything, you need to dilute it quite a bit. Now, is this actually like a strong consideration whenever you, or is this a, let me see how to articulate this. When you drink orange juice, your body has a mechanism to neutralize the impacts of that acid. It does. So that is something that your body is capable of doing. Is drinking water overall a very positive thing for you? 100%. For every half a liter of orange juice, do you need to drink 7.5 liters of water? Probably not, because your body has mechanisms to basically neutralize that acid. But I think that it's a good visual to think about how much is needed to dilute something. Okay, I'm going to stop my share. I'm going to stop my recording.